In this video, I will go over a summary of the different types of destabilizing interaction that are found in cyclohexane and substituted cyclohexane, to be more specific. And so, depending on the position of the groups and the amount of substituent as well, they can interact with each other and give rise to different types of steric interaction, and therefore can destabilize the molecule. So first, the first type of interaction is something we call the A interaction or the A value. So this A value right here, so that would occur whenever we have an alkyl group interacting with the other hydrogen that are 3 carbon away, and they both axial. So a lot of time we refer to this as A13 diaxial interaction. And again, so the two, when we have an alkyl group on the axial location, it can interact with the hydrogen that are 3 carbon away that are also on the axial interaction as well. So this is called the A13 value. And another types of interaction is something we call the G value or GR. And this happens whenever we have two alkyl group located on 2 carbon away. So therefore we also call this to be G12 as well. And when the two groups are on the equatorial position, so again, only when they're in equatorial position that we would have this one right here. So here in this case, this 2R group, 1 and 2 carbon away, both of them are equatorial and they can interact with each other. Now, depending on the interactions and the nature of what this alkyl group would be, to add the interaction together, so the total destabilizing energy equal to GR and GR prime, depending on what this two value will be. And we'll be given this, how to look up this value right here in a little bit. But then that is how we can calculate together how much destabilizing energy when we have one of this G value. Now, here's something to take notice right here, very important with the 1-2 location. So only the 1-2 di-equatorial position would interact with each other, and that is included in calculation. Okay, if we were to have the 1-2 equatorial and axial location, we would omit that. We do not include that, although they do interact with each other. But as the ring flip, this interaction right here will be maintained in the other flips structure. So therefore, we will be omitting this in calculation, because again, what we're trying to do is to calculate the difference in destabilizing energy between the two conformations. And if they both have them, so why include them? So that would happen when we have the two group, one is equatorial and the other one is axial. For an example, here the case right here, where we have this 2 methyl group, they're 1 and 2 carbon away. This one right here is equatorial, and this one right here is axial. So they do have that Gauss interaction right there. So yes, they do have it, but let's see what happened. When we flip this to the other conformation, now this is what happened to the 2 methyl group. And we can see that they will still be 60 degrees from each other, and we still would see this Gauss interaction right here. So basically this interaction will be maintained as the ring flip, and this is why that we do not need to include them, because both conformations will have them, and that will not contribute to the difference in energy between the two conformations. Okay, but only when they are di-equatorial that we need to include them, because as the ring flip, this interaction right here can change and will not be maintained anymore. So this is why that we only need to pay attention to 1-2 di-equatorial interaction. And lastly, the other value that we have seen already is called the U value. So this U value right here is, we call this U because it adopts this shape right here that look like the U. So whenever we have 2 alkyl group or can be any other group that are 1, 2, and 3 carbon away from each other, we can call that a U value. And basically, depending on the nature of what this R group would be, to calculate how much interaction they go into this, we can see the following. Also, it equal to a UR plus a UR prime, depending on what this two value would be. And we also need to consider the following. Each of this R and this R prime right here are also interacting with this hydrogen. So therefore, we also will need to include the AR and AR prime as well. Now, so in this case right here, we have to plus 1/2 of this. And the reason why, because of the following. When we given an AR value, the AR value is a value that corresponds to the R group interacting with two of the hydrogen. Okay, so let's say here the hydrogen right here, then the A value describes the interaction between this group with both of this hydrogen. But in this case right here, because there's only one hydrogen, so this is why that we have to multiply this by 1/2, because we have only one of that interaction. And again, this is simply because the value given is for the interaction between the group and two hydrogen, but we have only one, so therefore one of the A value. And now the other will then be the other one to describe the interaction between the R prime and the other one. So this is how we can calculate how much interaction is involved when we see the position of this group as follows. And now here are the value, the table that will tell us how much energy are being involved in these different types of interaction. And again, we can break them down into the A value, the G value, and the U value. And again, depending on what the R and R prime would be, then these are the different energy that they would have. For an example, let's say here we have 1G. Let's say we have here a metal group, and here is a iodine. Then we can see, to figure out how much energy involved, we will be taking a G of CS3, so we will go to G, and now a CS3. So here in this case right here, we don't have a CS3, but the CS3 and this CHR right here are together. So whether it is a metal group or a longer alkyl group, they will be the same thing. And that will then be 0.4. And now it will be a G of an iodine. So that would then be this value right here. So we can add these two values, and that will tell us how much destabilizing energy between a CS3 and an iodine will be. Okay. And now let's do an exercise, do some practice to make sure we know how to do this. So let's do now an example number 2. What happens when we have a 1,4-dimethyl cyclohexane? Because this is one unique example that we have not discussed before. So let's do this problem together. So in this case, let's start by drawing the first conformation. And again, you can make sure you draw your cyclohexane well. And now connect the dots. And we can label this 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. On carbon 1, we have a metal, a CH3 group point down. So the down position on this group right here in this chair will then be the equatorial location. Okay, and that means the hydrogen will then be pointed up. And carbon number 2, this hydrogen, so let's put them in. And on carbon 3, this will be the position of this hydrogen. And now on carbon number 4, we have another CH3 group. In this case right here, it is pointing up. So we have to go to this carbon, and the up position here will then be the equatorial position. So there it will be. And that means the hydrogen will then be pointing down. And now let's put in the rest of the other group. So that would be the first conformation of this molecule. And now let's calculate to see how much energy that it has, and see if we can recognize any of the types of interaction that we have learned already. And here in this case right here, there's none. And we happen to draw out, starting out with a less stable conformation, because again, this do not follow anything that we have learned already. These two CH3 right here are 4 groups from each other, and this is not anything that of the types of interaction that is significant that matter. So overall total ED here equal to 0 kcal per mole. Now let's flip this and see what happened. So when this flip, so let's draw the flip chair of it. So there it is, carbon 1, 2, 3, 4, 5, and 6. Now on carbon 1, the methyl group here, initially it is equatorial point down, so now it becomes axial point down when it flips. And now for the hydrogen, there's nothing, so let's draw them out. In carbon 3, let's also draw them out as well. And on carbon 4, we have this methyl group, and right now this is equatorial and point up, so this will then become axial and point up. And here it is, the other group. Okay, so now that we have drew this out already, let's now analyze to see if this have any of the interaction we have mentioned already. So in this case, we do see this again. Anytime we have alkyl group or any type of group at the axial location, that's something for us to start looking at. So in this case, we can see that there is an A value, right? An A interaction between this CH3 and that. And down below here, we have that same thing as well to this other two hydrogen. So there you go. Those are the significant interaction that we can find in this conformation. So now the total ED for this equal to the following. So we have an A. In this case right here, we will call this an A13. Okay, and the CH3, ACH3. So again, A is whenever we have this group, and again 3 carbon away on, then we have those hydrogens. So that will be called an A value right here. And we have 2 of them. This one as well, another ACH3. And we will go back to this table and we look them up. So we have an A value involving a CH3. And again, the CH3 and CHR, whether we have a bigger alkyl group that are linear without any branching on it, then the value are all the same thing. And again, please be noticed the thought following. This value right here is given for when this alkyl group is interacting with both of this hydrogen. Okay. So for each of the hydrogen, it will then be 1/2, which is 0.9. But the value given right here is for both of this hydrogen. So in this case, we have 2 of those. And this is now 1.8 kilocal per mole. And this one right here is also 1.8 kilocal per mole. So adding together, the total ED for this will then be 3.6 kilocal per mole. So very easy for us to see that between these 2 conformations right here, this will then be the more stable one.